Yeah.
Okay, sorry.
So that's that. Then what? So I'm trying to think here. Second here. What's our assumption? We're assuming f is equal. So in the forward direction, we're assuming f is equal to f1 plus f2 da, 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 almost everywhere. And all right. Okay, and then
Oh, and then we get
we have yes, we have f is equal to the sum almost everywhere. G is equal to the sum almost everywhere. Therefore, f is equal to g almost everywhere. And G, and so this means f is convergent in norm as well. So yeah. All right, fine. And then the converse direction, conversely, if f is equal to f1 plus f2 plus dot 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 in norm, then he says f is equal to g almost everywhere by theorem 2.75. Which one's that one? So many theorems. Oh, the one I didn't prove. The one I didn't prove last time at the end of class. Sorry about that. Yeah, that one says if fn converges to f in norm, then fn converges to g in norm if and only if f is equal to g in norm.
Oh, almost everywhere.
Almost everywhere. Yeah, excuse me. So we're assuming f is converging, f is equal to f1 plus f2 in norm. And we're trying to show that f is equal to f1 plus f2 almost everywhere. Let's see here. Oh, he's still using the same g from the first part of the proof, right? Because that corollary 2.54 holds for both. That's a precondition to the if and only if, you know. Like this g, it's the same g that you're just assuming f1 and f2 da, 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 are in a Lebesgue integral from the start. So it's not for just one direction or that. It's for both directions that we have built this g, and then he's like f is equal to g because. Well, because we have g is the sum of the f's, which then I think goes back to the other one we just talked about. Well, he's using the where'd that thing gone to? Sorry, we were just.
Oh, it's directly from
Theorem 2.77. 2.75.
Yeah.
Oh.
G equals.
How do we have fn goes to g in norm? I mean, certainly, well, we're assuming fn goes to f in norm. And we have that, so, and we also have that, and we also have the g, the sum of the f's goes to g almost everywhere.
Same.
So we have this.
Yeah.
And then because theorem 2.75, if and only if, so that then, if and only if, since we have this, then we get that Fn goes to G. So it's like this gives us this, then theorem 2.75 gives us then that Fn goes to, you know, my eyes keep skipping. Fn goes to, Fn goes to G in norm, but
is that because G, we have G equals F1 plus F2 plus F9 almost everywhere?
yes,
And by the very nice correlator that you basically granted.
right.
Yes.
Well, that's what, yeah, so we have that, which means we have Fn, okay, so let me just write it down. So Fn goes to G in norm, but let me remind myself what we're trying to prove. We're trying to prove that,
F2 is equal to F1.
we're trying to prove this implies that, right? So now we have, we have Fn goes to G in norm. Keep losing my place. Sorry, you guys. Let's see here. He says hence F is equal to F1 plus 2. All right, so hence F is equal to F1 plus F2 plus da 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 almost everywhere by theorem 2.7.7, which is which one? Theorem 2.77 is the one that says Fn goes to F almost everywhere, then Fn goes to G almost everywhere, if and only if F is equal to G almost everywhere. All right, which we proved at the start of class today. So that's if and only if. Let's see here. So we have,
So we get F equals G almost everywhere, but G equals the sum of F F's.
right. So I guess it's, we have, I think I've got things.
But G equals F1 plus F2 plus dot 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 almost everywhere by the correlator.
Right. Yeah, I think it's all here.
Yeah.
I keep losing track of where I am. My bad. Let us move along here. Nothing to see here. Let's move on, if you guys don't mind. So, let's see here. So this brings us to section 2.8, all right? So section 2.8 is on the fundamental convergence theorems. And so I probably won't try to prove these today, but I want to state them, all right? And then I'll think about my life and about whether or not we actually want to prove these in class, but here we go. First one is that the space L1R is complete. Right, meaning what? Meaning every Cauchy sequence of functions, I guess, Cauchy sequence in norm of functions converges, right? He says, in view of the previous theorem, the space L1R can be defined as the completion of the space of step functions with respect to convergence and norms. This looks like a very simple definition of Lebesgue integrable functions. However, in such an approach, the elements of L1R are not functions, and it's not clear how we can associate a function with an element of L1R. See, I think in this paragraph he should be using script L to be true to his previous work. Yeah, because
So we're starting.
we are of the agreement that L1R has functions in it. It is script L1R, which has the equivalence classes in it. So I disagree with this paragraph at the top of page 59, you know, anyway.
So we're really proving L, the script fancy L is complete.
I think this is fine. I just think his paragraph that follows it is not okay. Yeah. And then next theorem in the section is this: if Fn converges to F in norm, all right, then there exists subsequence Fpn of Fn such that Fpn converges to F almost everywhere. Ooh. Now that's interesting. So there's another relation between convergence in norm and convergence almost everywhere. Like if you have convergence in norm, then you can recover convergence almost everywhere subsequentially, apparently. That's neat. All right. Let's see here. What's he say? What's he tell us about this? He says theorem. He says this is 2.81, 2.82. Okay. And he says that these are attributed to. Oh man, I don't know if I can say his first name, but Frigyes. That is almost certainly not how you pronounce that. Frigyes? I don't know. And then last name, R-I-E-S-Z, Ries, maybe. And 1880 to 1956. All right. And he says more than this. He says convergence in norm has the following important property. Or we can say this: Fn converges to F in norm implies that the integral of Fn converges to the integral of F. All right. What's that, Audric?
No, more than that.
More than that?
Yeah.
What do you mean? Oh, in other words, the limit, so that is the limit, well, the integral of the limit as n goes to infinity of Fn is equal to the limit as n goes to infinity of the integral of Fn. So this is well, I wouldn't say this is not exactly an exchange of limits theorem here because, you know,
I was wondering how you got from
step
step 1 to step 2.
1 to step 2.
Like how the convergence in norm applies if the limits are interchangeable?
Oh, I think this is just admitting notation, right? So let's see.
Oh, is that limits on the functions that get to the end of this?
This is a different notion than this?
No, the limits in the inside the integral and outside the integral, right?
Well, I think that, okay, so let me, just a second here. So this, if I want to write this directly using limiting notation, it would look like this. The limit as n goes to infinity, right, of the integral of fn, parentheses, is equal to the integral of f, right? Agree?
Yeah.
But f is itself the limit as n goes to infinity of fn. So I think that's why they're the same. I think that's why this is the same as that, like that. Now, why convergence in norm implies that, I don't know if we've proved that yet. I can't remember. I know that uniform convergence of a sequence of functions allows you to exchange the order of the limit and the order of the integral, whereas pointwise convergence does not. You can have pointwise convergence such that like the limit of the function is 0, and yet the limit of the integrals of the functions is non-zero. This can happen. I might have showed you guys an example of that. I don't remember. This much I do remember. The example is in Rosenlicht, which I have in my office. I don't know if that answers your question, Audric, or? Yeah. Let's see here. So he says convergence almost everywhere does not share this property. And that makes sense to me because convergence almost everywhere is almost pointwise convergence. Almost. Let's see here. He says, on the other hand, in practice, it's often much easier to show that a sequence of functions converges almost everywhere than it is to show convergence in norm. And he says theorems 2.83 and 2.84 give conditions which are usually easy to check and at the same time imply convergence in norm. Now he's going to define non-increasing almost everywhere and non-decreasing almost everywhere to be just what you'd think. Okay. Fine, I'll write it down. Fn is non-increasing almost everywhere if the set of x in R on which Fn of x, right, is increasing is a null set. All right. So non-increasing almost everywhere means what it sounds like. Right? The set of points on which it's increasing is a null set.
And, sorry, I forget, well, we're talking about this length convergence. Is non-increasing strictly decreasing or is it just decreasing?
Increasing is strictly increasing. So non-increasing, it could be constant, it could be decreasing. The one thing it can't be is increasing. So I would say increasing in my usual language is strictly increasing.
Oh.
So, yeah. And we can do the same for non-decreasing almost everywhere. All right, anyway. He says the following theorem is due to Beppo-Levy. What a name. Beppo-Levy. I wish I'd found out about this name earlier. I could have tried for one of my children to be named Beppo. You know? It would have been epic. What's your kid's name? Beppo. You know. Everybody's named Beppo. 1876 to 1961. All right, so here it is, theorem 2.83. Excuse me. If Fn is sequence of integrable functions that is monotone almost everywhere. And the absolute value of the integral of fn is less than or equal to m for some constant m in the reals, of course, and all n in the natural numbers, then there exists an integrable function f such that hey, you're done?
Yeah.
Cool. I'll take it.
Thank you.
Thank you. Have a good weekend.
You too.
All right. See, now I can end class. I figured I might as well keep going with you guys if he's taking his test, right? Such that so sorry I went over, but fn goes to f in norm. Oh, and fn goes to f almost everywhere. Wow. Moreover, the absolute value of the integral of f is less than or equal to m. So this is the so-called monotone convergence theorem. So monotone means what? It's either non-increasing or non-decreasing, one or the other. You gotta pick your poison, one or the other of those. So this is the monotone convergence theorem. Let's see here. We have the Lebesgue convergence theorem, and then we have Fatau's lemma left in this section. I will start the next lecture by writing those. I think if you guys don't mind, I think we'll stop here for today. I might have I think there are children at the house. I need to go help. Isaac is having kids over tonight, so it's exciting. There you go.